Further complication arises when we have cyclohexane derivatives. So in this case, we have to use the chair conformation to analyze the reactions. And for an antiperiplanar requirement, E2 elimination means the leaving group and the beta hydrogen must both be in the axial position. So which of the two molecules below will not be able to undergo an E2 elimination, and why? So to figure this out, you have to draw the chair conformations for each one. So I'm going to call this A, I'm going to call this B. So with A, chlorine is up, so I'm going to go ahead and put it in the axial up. I'm just randomly deciding which one to start with here. And then H is down, H is up. Here, the methyl here would be up and the hydrogen would be down. So that's that carbon. This is to its left, that's why I put it over here. And then the CH2 here is to its right, so I put that here. So this is my alpha carbon, and these are my beta carbons. So this compound A should be able to undergo an E2 reaction because it has two beta hydrogens in the axial position when the halogen, the leaving group, is also in the axial position. So that one should be good. What about the next one? So I'm going to put my chlorine up because I know it needs to be axial up. Then Me stands for methyl, so CH3 is pointing down, H is equatorial up. Here H is equatorial up, CH3 is pointing down. Now here I have the leaving group axial up. And where are my beta hydrogens? That's these two things. But they're equatorial up. So this one will not undergo an E2 elimination because there's no chair we can draw where the chlorine, the leaving group, is axial up while the beta hydrogen is also axial down. So B will not undergo an E2 elimination. Here we have another problem. So rationalize the products formed in the following two reactions. So the first one you only get one product, but in the second one you get two products. And then it says one undergoes elimination much faster. Why is that? So here again we have to draw the chair conformers. So I'm going to draw my chair conformer. I'm going to put the chlorine here, which would be axial down, and the tert-butyl would be axial up. So the only beta hydrogen that could be eliminated, so here are my beta hydrogens. The only one that can be eliminated is the one that's axial. So that would be this one. So my base can only remove that. And then when I draw the product for that, that's what this is. So I can't get any other possible products because that's the only beta hydrogen that's axial that can be removed. However, when I look at the second example, okay, let's see. I draw my chair. I'm going to convert this to a chair. So I'm going to make this carbon here so that the chlorine is axial up because it has to be axial. Since this carbon's going to the left, that will be here, which means I'll have a hydrogen axial down and the T-butyl will be equatorial up. And then on the other carbon, I have two hydrogens, one axial down, one axial up. So this is this carbon. So I've got two beta hydrogen options that are axial. That's why I'm getting two products. So if my base comes in and removes that hydrogen in blue, then I get this product. Alternatively, if the base removes one of the beta hydrogen in green that's axial, then I get this product. So that's why I get two products, because in the bottom reaction there are two beta hydrogens that are axial. In the top, I just have one option. Then finally, why is there a difference in the reaction rate? The top one's slow, but the bottom one's fast. Well, let's look at the chair conformer That's the reactive conformer. And the top one, in order for us to have that leaving group axial, we've got to put that T-butyl group in an axial position. It does not like that. So that is not going to be present to a very great extent in solution because that's very high energy. In contrast, the conformer below here has that humongous T-butyl group in the equatorial position that's favored, and that means in solution that will be the predominant conformer, and that's a lower energy conformer. So as you can see now, there are many, many factors to consider with these E2 reactions. You want to first identify where are the beta hydrogens. Then ask yourself, is this base small or is it bulky? Could we get a lot of different alkenes? And will we favor the Zaitsev product or the Hofmann product? And then finally, what about the stereochemistry, given the anti-periplanar requirements? The only way to master this material is to do lots and lots of practice problems. Here is an animation of the E2 reaction. So we've got our strong base, and it's going to grab a beta hydrogen at the same time that the leaving group leaves and the double bond forms. And there's two different beta hydrogens it could use. So it's going to now, this next one, remove the other possibility. So test your understanding. Which of the following is the mechanism for the E2 reaction? Now for this, can you identify how many beta hydrogens the molecule has? So first you want to identify the alpha carbon, and then you want to identify all of the beta carbons. So that's one carbon over. And then count up the hydrogens on those carbons. Which of the following statements correctly describes an E2 reaction? The rate is equal to the constant times the concentration of the base. The rate is equal to a constant times the concentration of the base times the concentration of the alkyl halide. The rate is equal to the constant times the concentration of the alkyl halide. The reaction occurs in 2 or more steps. And 5, the beta hydrogen and the leaving group must be anti-periplanar. Consider this elimination reaction shown. It will give a major product and a minor product. What is the major product? What is the minor product? The options are A, B, C, and D. Now consider this reaction. Look at the base used. What will the major product be? What will the minor product be? So here I'm talking about Zaitsev versus Hofmann products. Finally, and this is a tough one, can you figure out the product of this E2 reaction? You will have to draw Newman projections. So you want to have the beta hydrogen and the chlorine atom anti-periplanar in an eclipsed conformer. So you first have to put this into a Newman projection, and then you have to analyze that Newman projection and figure out what groups are on the same side and draw the corresponding alkene. And that will be it for this video.